Hello everyone. In this video, I would like to go through the last slide of the whole semester and talk about a different parallel processing technique. Through the whole semester, we have introduced a lot of different things, including computer architecture, general computer organization architecture concepts, including pipeline processor, including MIPS assembly code, and we did a lot of quite a few different lab programming lab for MIPS assembly code programming. And we also introduced a high performance memory design, such as cache memory and virtual memory technique. We have also introduced error detection, error correction technique. So the last thing I have to talk about is parallel processing technique. In general, there are different types of parallel processing technique. So we have spent a lot of time for pipeline processor and understanding the basic structure of the CPU, the data paths of a given CPU, and how the pipeline processor was designed. So this is actually one important part of parallel processing, but there's also some other high-level parallel processing technique as well. So I would like to go through some of those concepts. I have posted a final exam review topic list. So please watch the first video of week 15. And so this will be the last video, the last lecture for the whole semester. And in week 15, you have two separate things. One is the parallel processing technique video, which is this one, and the other one is the final exam review topic list. So please watch that video if you haven't, and then you have a general idea on what is required for your final exam. So for this slide, for parallel processing technique, we only require you to know the basic concepts for a final exam. So basically, in your final exam, you will see at most a couple questions asking about the general concepts about parallel processing. Okay, so but those are important concepts for you to know. So it's impossible for us to as we have a lot of a big focus on assembly coding for this class required by the university. So it's impossible for you to go through all the high performance processing technique. For the high performance processing technique, in future we hope we could have one more computer science class build name with the name high performance computing, and that will be a upper division class. So for that kind of class, then we will focus on more about high performance computing and different parallel computing techniques. All right, so for parallel processing technique, there's different levels of parallelism. So first of all, instruction level parallelism, data level parallelism, and even high level parallelism. So you might not hear this, you might heard this before. So when people talk about parallelism, they actually have a lot of different level. They actually have different level of parallelism. So they could refer to the instruction level parallelism, data level parallelism, or could be even high level parallelism. So the pipeline processor is relatively a lower level parallelism technique that we have introduced. So there's also some other high level parallelism techniques such as multi-threading, multi-core computer. So almost everyone is using a multi-core processor right now in modern computer. Most of them are multi-core processor, right? And a lot of us will you have maybe some of you had the experience of using multi-processor or cluster, so cloud computing resources. So all those things, they belongs to the high-level parallelism technique. So all these technique, including from pipeline processor to cloud computing or GPU. So all these techniques are considered to be how to improve the performance of modern computer. So usually people call this as high performance computing topics. high-performance computing topics. So as I told you, I really hope in future computer science, we could make a new class called high performance computing. We had that class like many years ago, but it's not currently offered. So it's also really important for students who would like to do hardware engineering job in future. So let's look at the different level parallelism. So we have learned pipeline processing technique before. So when you look at the pipeline processing, so if you look at this figure, the pipeline processing technique, we are actually doing different jobs. So if you could call them jobs. So we're kind of like executing different instructions in different parts of the instruction at the same time. So along the timeline, we are actually executing different things at the same time, right? So the basic idea for parallel processing is along the timeline, you would like to implement multiple things at the same time. So what is data level parallelism? What is data level parallelism? So the data level parallelism, such as GPU is a really good example as data level parallelism. But a lot of other computers, modern computer, even not really advanced computer, small microcontroller, some of them do have data level parallelism. So the data level parallelism actually means you could execute multiple data at the same time. And usually, such as some computer could have like a vector, architecture. So we'll introduce those examples later in this slide. So for example, if you are processing a few numbers all together, and each of them is 8 bits long, or each of them is 32 bits long, for example, but you're actually doing the same calculation. You're actually doing exactly the same calculation of quite a few different data at the same time. And this kind of technique is called data level parallelism. So a vector machine is a perfect example for data level parallelism. So instruction level parallelism, that actually means along the same time, at the same time point, then we are executing different things. We're executing different tasks, such as instruction level parallelism, such as a pipeline processor. So we are actually performing, for example, the instruction decoding, the instruction fetch, the instruction executing for different instructions at the same time. So this is a perfect example for instruction level parallelism. And we'll introduce some other examples, some other technique as well in this slide. So thread level parallelism. So this is comparing with the data level, instruction level parallelism. Then thread level parallelism is kind of like a higher level parallelism, right? So it's not really directly related with the detailed hardware structure. So of course the hardware structure is really important here, but it's more thinking about how to divide the different tasks. So it's not necessarily that we want to divide each instruction into into a few different stages, but we could divide either instruction, or we could divide like a piece of program. We could divide a piece of program into a separate pieces, and we could perform the different task, the different pieces at the same time. And there's also different types of thread level parallelism, such as coarse grain multi-threading or fine-grained multi-threading. So we'll talk about those examples in this slide. But in general, we do have different levels of parallelism, including data level parallelism, instruction level parallelism, thread level parallelism. So for the final exam, such as, for example, if I gave you a term such as pipeline processor, for example, and I could ask you, is this a thread level parallelism technique or not, right? So of course the answer is no. So I can ask you some really basic question about if you know, to test if you know what kind of parallelism this is. So for example, so let's start with the instruction. Let's start with the instruction parallelism. So instruction parallelism pretty much talking about focusing on how to execute different things, the different detail task, which is inside of the instruction or the instruction among different instructions, how to parallel process, how to perform the parallel processing inside of the instructions in one instruction or in multiple instructions. So for example, increasing the depth of pipeline processor is a good way to implement instruction level parallelism, because in pipeline processor is the most typical and pretty much instruction level parallelism. ILP is talking about pipeline. So pipeline processor is the most typical example for instruction level parallelism, because we're actually doing different things inside of the instruction at the same time, right? So if we increase the depth of the pipeline, having more stage in a single instruction, then of course we could execute multiple things at one time, right? And so increasing the depth of the pipeline is a good way to implement instruction or improve instruction level parallelism. And another way we could implement or improve the instruction level parallelism is called multiple issue. So the issue here is a verb, okay? So multiple issue means you can actually try to start multiple instructions at the same time. Right? So instead of starting one instruction or so this is a little bit different with the pipeline processor. If you think about the pipeline processor, so what we're doing is kind of like, stage. You could have a few stages for one instruction, and you stack them together. To have like a parallel parallel process at the same time, but you actually start with one instruction, right? So for a multiple issue computer, then what we do actually, you could view it as like a package. So you're kind of like selecting a few instructions, instruction 1, 2, 3, for example, 5. So you could have instruction 1, 2, 3, 4, and they could all start at the same time. So you could make a group. And start them at the same time, and you could consider which one should I execute at this time, which step. So inside of each instruction, then of course you still have a few different stages, and then inside of this whole package, then you could consider that I could execute stage 1 of instruction 1, stage 2 of instruction 2, or stage 1 of instruction 3, select the different things to execute at the same timeline. So this is called multiple issue. And there's two types of multiple issue computer. One is called static, one is called dynamic. So the static multiple issue computer actually, just as the previous figure I draw, so you could actually select a group of instructions to execute them together, right? And they could not have any data relationship or dependency, for example, right? So this actually depends on your compiler. So we could definitely do a good job to select. For example, if you have 100 mailing instructions in one application, so you could have many instructions, and then it's not a big deal. It's not really hard for the compiler to select a few instructions each time to form a packet. Because you could easily find, for example, 10 instructions. They're totally not related with each other, and you could reorder them, and you could select them to use them as one packet and implement together, right? So we could also have very long instruction word. So it's kind of like a special format instruction. So in that kind of instruction, you could have a style of instruction set architecture that launch many operations defined to be the independent in one single wide instruction. So they think instruction we have is like a super wide. It's pretty long. It's pretty long. Okay, it's a pretty long instruction. And inside of that instruction, you could have several OP code. So it could, for example, I could have one instruction, and that instruction could means load a data from the memory and perform addition using ALU, and also store another piece of data into the memory. So a very long instruction could have multiple operations at the same time, right? So it's actually the similar idea, with the a packet of different instructions, right? So those are static multiple issue technique. So in order to execute multiple instructions at one time. And what is static? What is dynamic multiple issue? Dynamic multiple issue computer has a really popular name, fancy name called superscalar. So scalar machine basically means the the general computer that we have does not perform the dynamic multiple issue, dynamic multiple issue. But if you have some computer could perform the dynamic multiple issue technique, then this is called a superscalar. Inside of compare with scalar machine. So superscalar means advanced. It is also similar to pipeline technique. It is called an advanced pipeline technique that enables the processor to execute more than one instruction per clock cycle by selecting them during execution. So what's the difference? So it's again trying to implement more than one instruction, trying to implement multiple instruction at one time. So what's the difference between the dynamic, the superscalar, and the static multiple issue? So the most important difference here is during execution. So what does that mean? So if we would like to implement static dynamic issue computer, actually you select a few different instructions and you execute them together, right? And the superscalar actually does not need the compiler, does not need the software to perform this. So it is actually implemented by hardware. So you have a piece of circuit inside of your CPU. So that piece of circuit will automatically check and determine which multiple instructions can be executed together, when the program is being executed. So this is kind of like the static multiple issue is kind of like, oh, I have 1,000 things to deal with, and how can I do parallel? So I will divide them into packet, and I can execute one by one packet, another packet, third packet, things like that. And this one is you throw the whole group, the whole big program sequence into the computer, into the hardware, and the hardware determines dynamically select whichever could be, I can select 3 of them, 5 of them, or 6 of them all together and execute them all together. So this is called superscalar, which is a really, really advanced and popular modern computer parallel processing technique. So when you have the hardware support, then things become so different, right? So it's much faster, of course. So there's also some, this figure, I will skip that, but I would like you to know the term, what is superscalar at least, okay? So I would skip the detailed structure. So data level parallelism. So those no matter dynamic or static, multiple issue or pipeline processor. So those are all instruction level parallelism. And what is data level parallelism? So data level parallelism mainly focus on the two most popular examples are multimedia extension, short vector, or vector instruction. So both of them refers to vector architecture. Both of them refers to vector architecture. So multimedia extension, this is kind of like a little bit older concepts compared with this. So it's not a really pure vector architecture, but still have the same idea of how to perform the data as a vector, how to perform different data as a vector. So that's why it is called a short vector. So what does it mean by multimedia extension? So for example, for a lot of application related with graphic or media, like image, video processing technique, the image, video processing applications. So a lot of the data, they're like 8-bit or 6-bit long data. For example, if you are dealing with a pixel, and a pixel, grayscale pixel could be, have the color level from 0 to 255. So you actually will need only 8 bits to represent the color level of a gray scale pixel. And if you have a color pixel, then you will have 3 of those 8 bits. So you don't actually need a 32-bit or 64-bit word to represent the data, but you have a bunch of those data. So you have many pixels for one image, for example, right? So if you have a lot of similar, so all the data, they have similar size, they have the same size, but each of them is kind of like short. Each of them is kind of like not really long. So how people could make this more efficient? Because for multimedia application, like all the pixels, they usually will go through all exactly the same process. For example, you need to add all of them by certain number. You need to divide them by certain number to perform normalization, and you need to perform a Fourier transform for all the pixels, for example. So as they're all used by to perform the same calculation, and each of them is short, so then multimedia extension come out. So it's actually a special type of instruction or special type of architecture. For example, so you could have a 64-bit wide ALU circuit, right? So your ALU circuit could generally handle 64-bit 64-bit data. So you either have A and A plus B, and each of them is 64-bit long, but you could actually have many 8-bit long data, and that way you don't actually want to waste the 64-bit input, right? So instead of performing the 60-bit data, 2 of the 64-bit data, we could simultaneously operate on a few 8-bit data. So how many of them we could do? We could do 8 of the 8-bit, right? So each of them is 1 byte long. Then we could actually calculate 8 of them all together, right? So, and then this actually forms a vector. This is actually looks like a vector. So a single 64-bit ALU hardware, you could will it such as a smaller parallel ALUs. So it could a 64-bit ALU then could form 8 bits. So 8 of the byte ALU. So you could try to understand the big ALU becomes some smaller ALUs, and all the smaller ALU, they actually perform parallel processing altogether simultaneously, right? So, and then what is vector architecture? So the vector architecture is really similar to this idea. So originally people use the original computer designed like only including the pipeline process, for example, and does not have any other technique to perform parallel computing. And then people figure out, oh, a lot of the time we're actually dealing with the same calculation for all the same data, and the data is kind of like a short. So why I don't process all of them together, right? So this is kind of like the most classical data level parallelism become from the to satisfy the need of multimedia data. To satisfy the need of multimedia data. And later on, people have more and more complex calculation applications. And then the vector architecture come out. So the vector architecture is compared with the multimedia extension, it's kind of like a a pure vector idea. And this one is not a pure vector idea. So usually multimedia extension means, so in your general instruction set, you may have a few instructions. That are only designed for multimedia process. So it's kind of like an extension or add-on feature, additional feature to the original instruction set, to the original hardware architecture. So the vector architecture is a pure vector idea. So collect the data elements from the memory and put them in order into several registers, into a large set of registers, and then operate on them sequentially in the register using pipeline executing units. So how the vector architecture look like? There's an example here. So you actually use several registers, and for example, we have quite a few elements, such as so the data from number 0 to number 12, for example, and then and I have four lanes inside of my hardware. So including each line, they look exactly the same. So you have the same ALU lag calculations, such as addition, multiplication. So you have like the same calculation units, and each of them deal with different data. So for example, if I have 12 different data, and I can select 3 of them to put in lane 0, and another 3 here, another 3 here, another 3 here, and then they all perform the same calculation. So of course you have more powerful hardware, right? So when you have more powerful hardware, so the calculation part, they look exactly the same, but you could actually use a big piece of load and store, to load all those data together and store all those data together. So when you are moving the data, communicating with the memory, then you might want to move a big piece of data together, because you are usually dealing with a big piece of data, not instead of a small piece of data. And this is especially helpful if you're processing multimedia data, such as image and videos, right? And then all of them, they actually need to process the same way. Be processed the same way. So this is called vector architecture. So when we compare the multimedia extension with the vector architecture, so the vector architecture sometimes is called a single instruction, multiple data, because each single instruction is trying to execute multiple data, right? So it's easy to understand what is single instruction, multiple data. And you compare with the multimedia extension with the vector instruction. So the biggest difference here is, for the vector machine, we actually have separate all the separate separate hardwares, right? So you cannot like have different lanes and they all do the same thing. And different piece of data they're sending to the different location, right? So, but for multimedia extension, you are using one instruction, one ALU, actually to perform a few pieces of one data, right? So that's why so the multimedia data, of course, is an extension of the instruction set. The multimedia instructions specify a few different operations, but the vector instruction actually specify a lot of different operations, because you will have a lot of freedom, a lot of flexibility to perform whatever you want, right? So there's it's much more complex. So the vector machine could perform a lot of different operations, of course. And the multimedia extension is only a few different things you added to your original instruction set. So such as I would like to perform a certain multimedia calculation to, so you could use your existing hardware to perform just a little bit different with the original usage. So the number of elements you could operate on is specified by the OP code of your multimedia instruction, but how many elements we are executing, it depends on the hardware. structure for a vector machine, right? Because we have a few different registers and we actually use a bunch of them together. So of course, how many data we could process depends on the hardware architecture, depends on the number, the special register in the hardware, in the vector architecture. So both of them have the flexibility of data with the width of the data, right? Both of them are performing data level parallelism, of course. Both of them are performing data level parallelism, of course, but they are different. So and how about high level parallelism? So what about high level parallelism, such as thread level parallelism, multi-core processor, multiprocessor? So what does what do those terms mean? So you probably have heard this somewhere before already. So like a cluster, multiprocessor. So what does that mean? What does each of them mean? So we'll go through some general concepts. So first of all, for high-level parallelism, we need to be able to differentiate what is software understanding of the parallelism and what is the hardware understanding of the high-level parallelism. So when we talk about high-level parallelism, it could be at really different. It could be really different, many different things. So the instruction level parallelism, data level parallelism, usually they're straightforward. And if you talk about data level parallelism, then people immediately think about vector machine. People immediately think about vector machine. If you talk about instruction level parallelism, then everybody know pipeline processor, right? However, so when people talk about high level parallelism, it could refer to so many different things. It could refer to many different things. The toppest level could be application perspective. So what is how the hardware people think about application level parallelism, and how the software people think about application level parallelism. So you might hear two terms. So this is kind of like too many terminologies here, but I really want to mention those because you might need to know this. You might eventually have a chance to learn this concurrency, for example, in your operating system. You might learn that in your operating system, but right now I just want to throw out the terminology that you know at which level those terminology is. Okay, this is not required for our class, but I will not test you on this, but it's better for you to know that. So so when people think about software, so the software perspective of application parallelism could be sequential. Could be so certain calculation is considered to be sequential calculation, and certain calculation is considered to be concurrent calculation. Such as if we're using a single core processor to perform matrix calculation. So even you might think about, oh, when I use MATLAB and the matrix calculation is actually performed, then this is parallel processing. But in software level, this is still a sequential operation. This is a sequential operation, even you are operating on a matrix. But what is concurrent? So for example, your operating system. So if you're using our operating system, you are using that every day. For example, right now I'm using my Zoom application, I'm using my operating system. I may be playing the music at the same time, and I may be using a PowerPoint, Microsoft applications. So my operating system does not need to handle or does not need to be active all the time, right? So sometimes I need to find a certain file, then the operating system helped me to find a certain file. And then sometimes I'm playing the music, and sometimes I'm running a program. So altogether, there's multiple applications that take the results of my hardware. They take the results of my CPU at a different level, but they all happen together, right? So this is the really, really top level of the parallelism, and this is called concurrent. Right? So of course, your operating system is running all the time, but at the same time, so at current time, I need the Zoom application to be more active, and the Zoom application use more resource right now, right? So if you're running a program, so your program actually takes more resource of your hardware. So of course, the concurrent means you are doing different tasks, high level tasks. You are running different applications at the same time. So when we talk about hardware parallelism, so then we pretty much refers to serial and parallel. So the serial is different with the sequential here, okay? So the serial actually means you're doing things one by one. And parallel means you're doing things at the same time using your hardware. You're doing multiple things using one piece of hardware at the same time. So for example, so if we're performing matrix calculation using one single call, then this is a serial processing. If you're performing the matrix calculation using multiple piece of the hardware, multiprocessors, then this is of course parallel processing. Right? So this is actually thinking about, in the really top level, high level application perspective, then what does it mean for parallel? What does it mean for parallel? Okay, so there's also another term called parallel programming. And when you see parallel programming, then this is something totally different with the parallel technique we are talking right now. So parallel programming could be super, super hard because you are trying to consider one single application, one single program. How can I divide one single program to be a few different pieces and then perform all of them together? And remember, inside of one single program, then you could have a lot of dependencies about the current step, the next step, the last step. So everything is related with each other. And then if you want to do things in parallel, then that would be super hard. So this is totally another topic. And I hope, in general, you understand what does parallelism mean, and at different level and different perspective of the parallelism. Okay, so again, this page is not totally required. It's not typically required for us, but I would like to give this figure out, try to give you a little bit idea about parallelism can be so many different things. Okay, especially in high-level parallelism, when you talk about the application, when you talk about the software, then it's totally different with what we are talking, because we focus on the hardware design. So thread level parallelism is one typical parallelism, high-level parallelism. And the most important example is called multiple threading. So what is multiple threading? So the hardware multiple threading actually means we would like to increase utilization of a processor by switch to another thread when the current thread is stalled. So for example, the current thread here can be a task such as you're making coffee. So when you're making coffee, then you have a few steps: prepare the coffee, coffee beans, prepare the water, and start to brew. And then you might need to wait a certain time. Until the next step. And at that time, you do not need to waste the resource of your processor. You do not need to stall the processor, right? So then we could switch to another process. We could switch to another thread. Such as this thread is actually cleaning up the tabletop. The cooking top, for example. And after that, you could come back to this current thread and continue this task. So you could have multiple tasks inside of a process, and you could actually have many processes in a single application, such as your Zoom application, such as your email application, right? So the thread here is a really small concept compared with the process, and the process is a smaller concept compared with applications. Okay, so I hope you know. So this is actually a lower layer facing the hardware. So it's of course not a real how to say, it's not as low as like the pipeline level because it could be refers to different tasks and one task could include like thousands or millions of instructions even, right? But however, it's still a relatively lower layer compared with application, compared with multi-core, compared with multi-processor. So this is how the hardware could look like. So you could have multiple PC, start with different location of different piece of programs, and then you could have multiple multiple thread indicated by the different color here, goes through the multiple location of the whole hardware pieces. So they kind of like combined at a certain time and separated by different piece of hardware, but combined at a certain time as well, So I will skip the detailed hardware structure, but I would like to talk about two concepts, two examples for multi-threading. One is called coarse-grained multi-threading, one is called fine-grained multi-threading. So the coarse-grained multi-threading means, so you could switch to another task, you could switch to another thread. So the CPU, the hardware actually could switch to another thread after a significant event, such as a cache miss, right? So when you process the instruction sequence, you have many instructions, and then this instruction is a load, for example. And after that load, you have to wait a super long time because this load will need to read a piece of data from the memory, and you don't have it on the cache. And that will take you a lot of time, right? So you do not want to waste that part of time, and you could switch to another thread and then come back later again, right? So this is called a coarse-grained multi-threading. And the fine-grained multi-threading could be, you have many instructions, and then this current instruction will need to generate a few stall, for example, and you really don't want that stall happen, and you could switch to another instruction in another thread and come back again, and you could implement a couple instructions in another thread and come back again. So this is kind of like more flexible, and then you divide the whole sequence into smaller pieces. And a really good figure can be this. Once you have multiple function units inside of the hardware, and then the fine-grained multi-threading could perform different tasks. So different color represent different tasks at the same time. So along the execution time, then you could actually perform, the first task for a certain time, the second task for a little bit time. So like one instruction, for example, from the first task, two instruction from the first task, two other instruction from the second task, and one instruction from the third task even. So you could switch more often. And the coarse-grained here is you kind of like finish one piece of one detailed task, or one piece of a few events inside of the current thread, thread, and then switch to another. For example, so you're performing the current thread right now, executing the current thread right now, and then after we figure out, oh, there is a cache miss. So we should actually, pad into other things in the timeline. So we start to execute another piece of program, instead of waiting for a long time. But you do not actually switch instruction by instruction, right? So we cut it piece by piece. So this is a general idea. So you actually have a more often switch, or a more flexible switch. if you're doing a fine-grained multi-threading. So this is only, you know, at different level, but you're doing actually the same thing. So we are implementing or running a few sequence of programs, a few sequences of instructions at the same time, a few sequences of programs at the same time. So that's why you have multiple PC, because you start all together at different location from different piece of programs, right? So, and then that's the like the lowest level, high level parallelism, the lowest level, high level parallelism. So a little bit higher level could be multi-core processor. So what is multi-core processor? Such as i7, Intel i7, right? So you have multiple chips, multiple CPUs, right? So then this is a really typical example we use every day. Almost all the microprocessors today in desktop and servers, they're multi-core processor. So job level parallelism could be running different independent programs simultaneously on a multiple processor. But a multi-core processor is different. It's different with this, right? So we want to implement job level parallelism, you know, a thread level parallelism. Multi-core can be used all together. So we hope the ideal case will be, you know, in every level, then we are doing parallelism. But this is really hard. So you might have heard a few other multiprocessor concepts. So one is called shared memory multiprocessor. What does that mean? So shared memory multiprocessor, you will have a few different processor, and they have their own cache, but they all share a same memory. So they are sharing the same memory. So that's why it's called SMP, shared memory multiprocessor. So what does that mean? So you have the control, you have the you know, ALU, the calculations, those execution pieces inside of the processor, and you have each several of those kind of those kind of circuits, but they share one memory. So they physically share one memory, but they all have their own virtual memory address, right? So each of them assume they have their own memory, but they all share same big memory. So, but the interesting concept, which is similar to this, but a lot of people will get confused about this, is called cluster. So a set of computers, they are connected over a local area network that function as a single large multiprocessor. It's called a cluster machine. So the cluster machine actually has many different processors. Okay, so there's many different processors. They are separate. They do not share a memory, but they communicate with each other. So you could have a cluster machine help you to perform a really big complex task, and each computer inside of it, they could be responsible for one piece of work, one piece of the whole application. But they are separate computers. Right? So when you compare the cluster with shared memory multiprocessor. So the shared memory multiprocessor, they actually share one piece of memory, so they do not have their individual memory. But the cluster machine, so each of them is one separate computer actually, right? But they are connected and they're organized together to perform a same task. So they could, I should not use task, a same application. So you could try to finish one same application using multiple computers, and because they are all connected and organized as a cluster. So this is the difference between the cluster and the shared memory multiprocessor. So it's pretty interesting to differentiate. A lot of people get confused with the two different ideas. Okay. So for cloud computing, it is like the most popular high performance computing technique people are using, especially, for example, for data analysis, big data, machine learning applications, and many, even my students, they will need to use cloud computing resources such as Amazon AWS, such as Google Cloud Platform. So what is cloud computing resource? So for example, if we have one server, then one server usually could have multiple processor in it. You could have multiple chip, right? Really big, really powerful computer, really powerful computer. But this is only called one server, one server. So one server can be made by multiple processor with high level, with advanced cache, multiple level of cache, for example, and then has a really powerful computing resource compared with a general desktop, but multiple servers actually could form a rack, Multiple servers could form a rack. So a rack could actually include, you could view it as a group of servers. So it is even more powerful, but that's why, because you have more machines, right? So, and cluster can be even with multiple racks. Cluster can be like a topper level on top of the racks, So what is cloud computing? So cloud computing actually is a technique, and people refers to cloud computing every day now. So you are using like a cluster like machine, right? So you're using the cluster computing resource, and the cloud computing technique offered today actually allows you to use the different machine at a different location, and the machine are actually with a really powerful computing resource. Each machine inside of the cluster is actually really powerful machine. It's actually a really powerful machine. So such as if you use Google Cloud Platform, so for example, sometimes I use Google Cloud Platform for my machine learning project. So so you have like a lot of different machines you could select, a lot of different computing resource, and they could be physically at all different locations inside of US. And then you could actually select the most powerful machine you want, and then send your request to the cloud, and the cloud is a kind of like refers to the technique, helps you to manage or put your task to certain physical machine, help you to compute. So you do not necessarily know where the machine is, inside of the cluster, but you just take one piece of the resource of the cluster, right? So this is cluster and computing, cloud computing. So graphic processing unit, GPU, is a really powerful computing technique currently, especially for graphic and multimedia process, because it actually perfectly implement the data level parallelism. And you could even have thread level parallelism. You could have instruction level parallelism, data level parallelism, thread level parallelism, implemented in one GPU. So that's why this could be really with high efficiency. So I think that's all the general terminology I would like you to know for this class, and that will help you prepared for any future upper level class about high performance computing. By now, so I have a few other pages listed here, but that's not required for this class. So I will stop here for this video, and this is the last lecture of the whole semester. And good luck for your final exam. If you have any question, feel free to contact me, and hope you all stay well and have a good summer.